The 500-meter aperture spherical radio telescope stands nestled in a natural karst depression in China's Guizhou province, its reflective surface spanning 500 meters across like a giant eye staring into the cosmos. When you look at aerial photographs of this structure, it's almost difficult to comprehend the scale. We're talking about a dish that could comfortably fit 30 football fields inside its collecting area. The sheer engineering ambition behind FAST represents something that sounds almost fictional, yet here it is, the most sensitive radio telescope humanity has ever constructed, listening to the universe in ways we've never been able to before. The story of FAST begins with one man's vision, astronomer Nan Rendong, who dedicated 22 years of his life to making this astronomical dream a reality. 22 years. Think about that for a moment. That's longer than many of us spend in formal education, longer than most careers. Nan Rendong spent more than 2 decades working toward a single goal, searching for the perfect location, designing the technology, overcoming countless engineering challenges, and rallying support for what many considered an impossibly ambitious project. The tragedy is that Nan died in 2017, just 3 years before FAST began its official operations in January 2020. He came so close to seeing his life's work reach fruition, but the universe had other plans. What makes FAST so extraordinary isn't just its size, though that alone is staggering. It's the combination of scale and sensitivity that sets it apart. FAST sensitivity is approximately 2.5 times greater than the Arecibo Observatory in Puerto Rico, which held the record for the largest single-dish radio telescope for decades until its tragic collapse in December 2020. That improved sensitivity means FAST can detect radio signals from cosmic sources that would be completely invisible to other telescopes. It can pick up whispers from the universe that other instruments can't even begin to hear. The location itself was chosen with meticulous care. Guizhou province features numerous natural karst depressions, geological formations created over millions of years by the dissolution of soluble rocks. These natural bowls in the landscape provided the perfect foundation for a radio telescope of unprecedented size. Rather than constructing an enormous support structure from the ground up, the engineers could use the Earth itself as the primary support, with the telescope's reflective surface suspended within the natural depression. This approach not only made the construction more feasible but also provided natural shielding from radio interference, as the surrounding mountains helped block unwanted signals from human civilization. The design of FAST incorporates innovative technology that allows its reflective surface to change shape. Unlike traditional radio telescopes with rigid dishes, FAST uses an active surface made up of 4,450 triangular panels. These panels can be adjusted by a system of cables and actuators, allowing the telescope to focus on different areas of the sky without having to physically move the entire structure. This gives FAST an effective observing angle of 40 degrees, far greater than what would be possible with a fixed spherical reflector. The receiver cabin, suspended 140 meters above the dish by cables, can move to different positions to collect signals reflected from different parts of the surface. Since beginning its official scientific operations, FAST has proven its worth beyond anyone's most optimistic predictions. The discovery of over 1,000 pulsars by November 2024 is nothing short of remarkable. To put this in perspective, that's more pulsars than all other telescopes in the world discovered combined during the same time period. We're not talking about a marginal improvement over existing technology. We're talking about a quantum leap in our ability to detect these fascinating cosmic objects. But what exactly are pulsars, and why does finding so many of them matter? Pulsars are rapidly rotating neutron stars, the ultradense remnants left behind after massive stars explode as supernovae. A neutron star packs roughly 1.4 times the mass of our Sun into a sphere just 20 kilometers across. To give you a sense of the density involved, a single teaspoon of neutron star material would weigh about 1 billion tons on Earth. These objects rotate incredibly fast, sometimes hundreds of times per second, and they emit beams of radiation from their magnetic poles. As the neutron star rotates, these beams sweep through space like lighthouse beams, and if Earth happens to lie in the path of one of these beams, we detect regular pulses of radio waves, hence the name pulsar. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish at Cambridge University. The signal was so regular, with pulses arriving every 1.3 seconds, that the researchers initially wondered if they might have detected an artificial signal from an alien civilization. They even jokingly called it LGM-1, for Little Green Men. Of course, they soon realized they were observing a natural phenomenon, but the discovery revolutionized our understanding of stellar evolution and extreme physics. Pulsars serve as natural laboratories for studying physics under conditions we can never reproduce on Earth. The gravity at the surface of a neutron star is about 200 billion times stronger than Earth's gravity. The magnetic fields are billions of times more powerful than anything we can create artificially. In these extreme environments, matter behaves in ways that push our theories of physics to their limits. By studying pulsars, we can test Einstein's theory of general relativity with extraordinary precision, investigate the properties of ultradense matter, and explore the behavior of magnetic fields in regimes far beyond anything accessible in terrestrial laboratories. Among FAST's discoveries are 177 millisecond pulsars, which are particularly intriguing objects. These pulsars rotate hundreds of times per second, with some completing a full rotation in just a few milliseconds. They're sometimes called recycled pulsars because they're thought to be old neutron stars that have been spun up to incredible speeds by accreting matter from a companion star in a binary system. The infalling matter transfers angular momentum to the neutron star, gradually increasing its rotation rate until it becomes one of these incredibly fast-spinning millisecond pulsars. These objects are so stable in their rotation that they rival atomic clocks in their regularity, making them useful as cosmic timekeepers. FAST has also discovered 157 binary pulsars, systems where a pulsar orbits another star. These systems are particularly valuable because we can use the orbital dynamics to measure the masses of the stars with great precision. In some cases, both stars in a binary system are pulsars, giving us what's called a double pulsar system. The first double pulsar was discovered in 2003, and it has provided some of the most stringent tests of general relativity ever conducted. The two neutron stars orbit each other every 2.4 hours, and the system is gradually losing energy through the emission of gravitational waves, exactly as Einstein's theory predicts. Then there are the 107 RATs, or rotating radio transients, that FAST has found. These objects are somewhat mysterious. Unlike regular pulsars that emit detectable pulses with clockwork regularity, RATs produce sporadic bursts of radio emission separated by long periods of silence. We're not entirely sure why these objects behave differently from regular pulsars. One possibility is that RATs represent an extreme form of pulsar nulling, a phenomenon where pulsars temporarily stop emitting detectable radio waves. Another theory suggests that RATs might have highly complex magnetic field structures that only occasionally channel radio emission toward Earth. Whatever the explanation, RATs represent a population of neutron stars that we're only beginning to understand. And fast sensitivity makes it uniquely suited to detecting these faint and sporadic signals. What really sets FAST apart is its ability to detect the faintest and most distant pulsars. Radio signals from pulsars are already extremely weak by the time they reach Earth, having traveled across vast cosmic distances. The signal strength falls off with the square of the distance, so a pulsar twice as far away produces a signal 4 times weaker. Additionally, radio waves passing through the interstellar medium, the thin gas between stars, become dispersed. Different frequencies travel at slightly different speeds through ionized gas, causing the radio pulses to become smeared out in time. This dispersion increases with distance, making distant pulsars even harder to detect. FAST's enormous collecting area and sophisticated signal processing capabilities allow it to overcome these challenges and detect pulsars that would be completely invisible to smaller telescopes. The implications of discovering so many new pulsars extend far beyond simply adding to our catalog of cosmic objects. Each new pulsar provides a data point for understanding the population of neutron stars in our galaxy. How many are there? Where are they located? What are their typical properties? These questions can only be answered through surveys that detect large numbers of pulsars. FAST is providing an unprecedented census of the pulsar population, allowing astronomers to refine their models of stellar evolution, supernova explosions, and the structure of our galaxy. Some of the pulsars FAST has discovered are particularly interesting because of their extreme properties. There are pulsars with incredibly strong magnetic fields, called magnetars, where the magnetic field strength reaches 10 to the 15th Gauss. That's 1,000 trillion times stronger than Earth's magnetic field. These magnetic fields are so intense that they affect the quantum vacuum itself, causing strange effects like vacuum birefringence, where empty space begins to behave like a crystal, splitting light into different polarizations. Other pulsars show glitches, sudden increases in their rotation rate. Neutron stars are thought to have a solid crust of extremely dense matter overlying a superfluid interior. Occasionally, as the neutron star gradually slows down due to energy loss, the crust and superfluid can become out of sync. When the difference becomes too large, there's a sudden transfer of angular momentum from the superfluid to the crust, causing the pulsar to momentarily spin faster. By studying these glitches, astronomers can probe the interior structure of neutron stars and the properties of matter at nuclear densities. FAST's capabilities extend beyond pulsar astronomy, though that's certainly one of its primary science goals. The telescope is also being used to detect neutral hydrogen gas in distant galaxies, study fast radio bursts, and even participate in the search for extraterrestrial intelligence. Neutral hydrogen emits radiation at a very specific frequency, 21 centimeters wavelength, and by observing this emission, astronomers can map the distribution of gas in galaxies and study how galaxies evolve over cosmic time. Fast sensitivity allows it to detect neutral hydrogen in galaxies much farther away than previously possible, providing new insights into the history of star formation and galaxy assembly across the universe. Fast radio bursts, or FRBs, are one of the most mysterious phenomena in modern astronomy. These are extremely brief flashes of radio emission, lasting just milliseconds, but releasing as much energy as the Sun does in several days. The first FRB was discovered in 2007 in archival data from the Parkes Observatory in Australia, and since then, hundreds more have been detected. Most FRBs appear to come from distant galaxies billions of light-years away, but the physical mechanism responsible for producing them remains uncertain. Theories range from exotic possibilities like colliding neutron stars or evaporating black holes to more conventional explanations involving magnetars or supernova remnants. FAST's rapid response capabilities and sensitivity make it well suited for detecting and localizing FRBs, helping to solve this cosmic mystery. The search for extraterrestrial intelligence, known as SETI, has been ongoing since 1960 when astronomer Frank Drake conducted the first systematic search for alien radio signals with Project Ozma. The idea is straightforward: if intelligent civilizations exist elsewhere in the galaxy, they might use radio waves for communication or other purposes, and we might be able to detect those signals. FAST provides unprecedented sensitivity for SETI searches. It can detect weaker signals from farther away than any previous telescope, expanding the volume of space we can search for signs of technological activity. In September 2020, FAST began participating in the Breakthrough Listen project, the most comprehensive SETI program ever undertaken, which is surveying 1 million nearby stars, the center of our galaxy, and the 100 nearest galaxies for signs of intelligent life. The international scientific community initially watched FAST's development with great interest, but access to the telescope was limited to Chinese researchers during its commissioning phase. This changed in March 2021 when FAST opened to international proposals. Scientists from around the world can now apply for observing time, making FAST a truly global scientific facility. This international collaboration is crucial because many of the most important questions in astronomy require observations from multiple telescopes using different techniques and observing at different wavelengths. FAST's radio observations can be combined with optical observations from telescopes like the Hubble Space Telescope or the new James Webb Space Telescope, X-ray observations from satellites, and even gravitational wave detections from LIGO and Virgo, providing a comprehensive multi-messenger view of the universe. The engineering challenges involved in building and operating FAST cannot be overstated. The construction required relocating more than 9,000 people from villages in the surrounding area to minimize radio interference. The remoteness of the site meant that all construction materials and equipment had to be transported over difficult terrain. The reflective surface itself required the development of new materials and manufacturing techniques to produce panels that could withstand the elements while maintaining the necessary precision for radio astronomy. The cable-suspended receiver cabin required careful analysis to ensure it could withstand wind loads and vibrations while maintaining precise positioning. Even the data processing systems required innovation, as FAST generates truly enormous amounts of data that must be processed in real time to detect faint signals buried in noise. Operating a telescope of FAST size and complexity is equally challenging. The reflective surface requires constant monitoring and adjustment to maintain its shape. The cables supporting the receiver cabin need regular inspection and maintenance. The sensitive electronic equipment must be protected from lightning strikes and power surges. The telescope is located in a region with distinct wet and dry seasons, meaning operations must be adapted to different weather conditions throughout the year. During the rainy season, moisture can accumulate on the reflective surface, affecting observations. Strong winds can make it dangerous to operate the suspended receiver cabin. Yet despite these challenges, FAST maintains an impressive operational efficiency, observing the sky night after night and producing groundbreaking scientific results. The data processing pipeline for FAST is particularly impressive. Radio telescope observations produce enormous amounts of data because they sample the sky at very high time and frequency resolution. A single observation might record the radio intensity in thousands of frequency channels, sampled thousands of times per second, potentially for hours at a time. This generates terabytes of data that must be stored, transferred, and processed. Finding pulsars in this data is computationally challenging because the dispersion caused by the interstellar medium means that the signal arrives at different frequencies at different times. The data processing pipeline must search across many possible dispersion measures, essentially trying to undo the effects of the interstellar medium to reveal the regular pulses characteristic of pulsars. This requires sophisticated algorithms and substantial computing power, and FAST has invested heavily in developing state-of-the-art data processing facilities. Machine learning and artificial intelligence are playing an increasingly important role in analyzing FAST's data. With so much data being generated, human astronomers cannot possibly examine all of it manually. Instead, they train machine learning algorithms to recognize patterns characteristic of pulsars, FRBs, and other phenomena of interest. These algorithms can sift through the data far more quickly than humans, identifying promising candidates for follow-up study. However, machine learning is not perfect, and human experts still need to verify the discoveries and ensure that the algorithms haven't been fooled by interference or other artifacts. The combination of machine intelligence and human expertise is proving to be a powerful approach to extracting science from FAST's data deluge. The relationship between FAST and the late Arecibo Observatory deserves special mention. For decades, Arecibo was the world's premier single-dish radio telescope, and it made fundamental contributions to astronomy, planetary science, and atmospheric science. Arecibo discovered the first binary pulsar, for which its discoverers received the Nobel Prize. It produced the most detailed radar maps of Venus and Mercury. It detected near-Earth asteroids, helping to assess potential impact hazards. When FAST surpassed Arecibo in size and sensitivity, there was a sense in which the torch had been passed to a new generation of instrumentation. Then, in December 2020, Arecibo's suspended platform catastrophically collapsed, ending its operations and devastating the astronomical community. The loss of Arecibo made FAST's capabilities even more crucial for certain types of observations, and there's a poignant sense in which FAST has inherited some of Arecibo's scientific legacy. Looking at the broader context, FAST represents China's emergence as a major player in big science and astronomy. For much of the 20th century, large-scale scientific facilities were concentrated in North America and Europe. The United States built massive observatories like Arecibo, the Very Large Array in New Mexico, and the Keck telescopes in Hawaii. European countries collaborated to create the European Southern Observatory with its facilities in Chile, including the Very Large Telescope. In recent decades, China has made enormous investments in scientific infrastructure, not just in astronomy but across all fields of science and technology. FAST is the most visible symbol of this investment in astronomy, but China has also built numerous other observatories, launched space missions, and established itself as a spacefaring nation with ambitions including lunar exploration and eventually human missions beyond Earth orbit. This shift in the global scientific landscape has important implications. Science benefits from diversity in approaches, ideas, and perspectives. Having major astronomical facilities in different countries, operated by different institutions with different scientific traditions, enriches the overall scientific enterprise. It also creates opportunities for international collaboration, as scientists from different countries work together to make sense of the universe. At the same time, there can be tensions, particularly when geopolitical considerations intrude into scientific collaboration. The free exchange of ideas and data that is essential for scientific progress can sometimes be at odds with national security concerns or political rivalries. Maintaining open, collaborative science in an increasingly complex geopolitical environment is one of the challenges facing the astronomical community. The discoveries FAST has already made in just a few years of operation suggest that we're only beginning to tap its potential. As astronomers develop more sophisticated observing strategies, as data processing techniques improve, and as the telescope's operation becomes even more refined, we can expect many more groundbreaking discoveries. Some of these discoveries will likely be completely unexpected. History shows that whenever we build instruments that significantly expand our ability to observe the universe, we discover phenomena that no one predicted. Pulsars themselves were completely unexpected when they were first discovered. Fast radio bursts were unknown until 2007. What other cosmic surprises are waiting to be found in FAST's data? One particularly exciting possibility is the detection of gravitational waves using pulsars. While ground-based gravitational wave detectors like LIGO detect gravitational waves from merging black holes and neutron stars, these facilities are sensitive to waves with frequencies of tens to thousands of hertz. But gravitational waves exist at all frequencies, and waves at much lower frequencies, in the nanohertz range, are produced by different sources, primarily pairs of supermassive black holes orbiting in the centers of distant galaxies. These ultra-low-frequency gravitational waves can be detected using pulsar timing arrays. The idea is to monitor a large number of millisecond pulsars, whose rotation is extremely stable, and look for correlated changes in the arrival times of their pulses. Gravitational waves passing between Earth and the pulsars would stretch and compress space, causing subtle, correlated variations in the pulse arrival times. By monitoring many pulsars distributed across the sky, astronomers can detect and characterize these gravitational waves. FAST's discovery of so many millisecond pulsars makes it an ideal instrument for pulsar timing array experiments, and it's already contributing to international efforts to detect nanohertz gravitational waves. In fact, multiple pulsar timing array projects around the world, including one using FAST data, have recently reported evidence for a gravitational wave background at nanohertz frequencies. This is exactly what we'd expect from the cumulative effect of many pairs of supermassive black holes throughout the universe, though the signal could also have exotic explanations related to the very early universe. If confirmed, this detection would open up an entirely new way of observing the universe, allowing us to study supermassive black hole binaries, test general relativity on cosmic scales, and potentially probe conditions in the first moments after the Big Bang. FAST's contributions to this emerging field of nanohertz gravitational wave astronomy could prove to be among its most important scientific legacies. The technology developed for FAST is also finding applications beyond astronomy. The techniques for active surface control, where thousands of individual panels are adjusted in real time to maintain a precise shape, have potential applications in large structures like deployable antennas for satellites or even future space telescopes. The data processing algorithms developed to find weak signals in noisy data have applications in communications, medical imaging, and other fields. The engineering solutions developed to construct and operate a massive structure in a remote, challenging environment provide lessons for other large-scale infrastructure projects. Scientific megaprojects like FAST often generate technological spillovers that benefit society in unexpected ways. There's something profound about humanity's commitment to building instruments like FAST. We invest billions of dollars, decades of work, and the talents of thousands of people to answer questions about the universe that have no immediate practical application. We want to know where pulsars are, what they're made of, how they behave. We want to detect signals from distant galaxies, understand the evolution of the cosmos, perhaps even find evidence of other intelligent life. These questions don't help us grow more food, cure diseases, or build better technology, at least not directly. Yet societies around the world continue to support this kind of fundamental research because we recognize that understanding the universe is part of what makes us human. We're curious creatures, and that curiosity drives us to build telescopes to peer into the depths of space and time. Nan Rendong understood this. He spent 22 years working toward a goal that he must have known he might not live to see fulfilled. That kind of dedication comes from a deep conviction that the work matters, that understanding the cosmos is worth the effort even if you personally don't benefit from the discoveries. There's something both tragic and inspiring about his story. Tragic because he came so close and yet didn't quite make it to see his creation operating at full capacity. Inspiring because his work continues, his telescope continues to make discoveries, and his legacy will endure as long as FAST continues to operate. When you stand at the edge of FAST's enormous dish and look down into that 500-meter expanse of reflecting panels, you're looking at a monument to human ingenuity and curiosity. You're looking at 22 years of one person's dedication, thousands of engineers and workers who made the construction possible, and the ongoing efforts of hundreds of scientists and technicians who operate the telescope and analyze its data. You're looking at humanity reaching out to touch the cosmos, listening for whispers from unimaginably distant places, trying to understand our place in the vast universe we inhabit. The radio waves that FAST detects left their sources years, decades, centuries, or even millions of years ago, depending on the distance. When FAST detects a pulsar 10,000 light-years away, it's detecting radiation that has been traveling through space for 10,000 years, having left the pulsar around the time humans were just beginning to develop agriculture. The photons have been traveling through the void all that time, passing by countless stars and nebulae, until by chance they encounter Earth and are captured by FAST's enormous dish, converted to electrical signals, amplified, digitized, and analyzed. In that moment, across 10,000 years and 10,000 light-years, a connection is made between a dead star spinning in the darkness and human astronomers trying to understand the universe. There's poetry in that connection, but there's also science of the most rigorous kind. Every pulsar discovered adds to our understanding of stellar evolution, tests our theories of physics under extreme conditions, and potentially provides a tool for detecting gravitational waves or other subtle phenomena. Every fast radio burst localized helps us understand these mysterious explosions of energy. Every neutral hydrogen observation maps the structure of the universe and the distribution of matter. FAST is a working scientific instrument generating real data that must be carefully analyzed, calibrated, and interpreted. The romance of cosmic exploration is grounded in the prosaic reality of science, detailed measurements, statistical analysis, systematic observations, and careful reasoning. The discoveries yet to come from FAST may be even more exciting than what has already been found. As the telescope continues to survey the sky, as astronomers develop new observing strategies and new ways to analyze the data, we'll likely be surprised by what emerges. Perhaps FAST will detect signals that point to new physics beyond our current understanding. Perhaps it will find evidence of exotic objects that theorists have speculated about but haven't yet been observed. Perhaps, and this is the most speculative possibility but also the most thrilling, perhaps FAST will detect something that makes us reconsider our understanding of whether we're alone in the universe. The search for extraterrestrial intelligence is perhaps the most ambitious application of FAST's capabilities. The probability of success is difficult to estimate because we have only one example of technological civilization, ourselves, and we don't know how common the emergence of intelligence and technology is in the universe. The universe is vast beyond comprehension, with hundreds of billions of galaxies each containing hundreds of billions of stars. Surely among those incomprehensible numbers, life must have arisen elsewhere. Surely some of that life evolved intelligence. Surely some of those intelligent species developed technology. These seem like reasonable assumptions, but we can't be certain. We might be extraordinarily rare, perhaps even unique. Or we might be in a universe teeming with life and intelligence, but separated by such vast distances that contact is impossible. Or perhaps civilizations like ours are common but short-lived, burning brightly for a few centuries before destroying themselves or evolving into something unrecognizable. We simply don't know. What we can do is look. We can point our telescopes at the sky and listen for signals that might indicate technological activity. We can be methodical and systematic, surveying large numbers of stars and galaxies, analyzing the data carefully, remaining open to the possibility of discovery while maintaining scientific skepticism. FAST gives us better capability to do this than ever before. Its sensitivity means it could detect transmissions that would be invisible to other telescopes. Its large collecting area means it can survey more stars in less time. If there's a technological civilization out there broadcasting at radio frequencies, FAST has a better chance of detecting it than any telescope that came before. Of course, even if no artificial signals are found, that result would tell us something about the universe. It would suggest that technological civilizations broadcasting at radio frequencies detectable by FAST are rare within the volume of space we've surveyed. That information would help constrain the parameters in equations like the Drake equation, which attempts to estimate the number of detectable civilizations in our galaxy. Null results are still results, and in science, they're often as important as positive detections. Should we expect to hear from anyone? The question is impossible to answer with confidence. Our sample size is one, ourselves, and generalizing from a single example is always dangerous. We've been transmitting radio signals into space for about a century, though most of those signals weren't intended as messages to other civilizations and would be difficult to detect at interstellar distances. Would another civilization that developed radio technology behave similarly? Would they deliberately try to signal their presence, or would they remain silent, perhaps fearing that revealing themselves could be dangerous? Would they use radio waves at all, or would they prefer other methods of communication that we haven't thought of? Would they even exist in a form we would recognize as intelligent? These questions touch on deep issues about the nature of intelligence, technology, and civilization. We tend to imagine aliens as being somewhat like us, perhaps more advanced technologically but still recognizable as intelligent beings building machines and exploring their universe. But intelligence and technology could take forms we haven't imagined. Perhaps machine intelligence is the rule rather than the exception, with biological intelligence being merely a brief transitional phase. Perhaps truly advanced civilizations transcend physical reality in ways we can't comprehend. Or perhaps the whole concept of advancement is misleading, and intelligence can take forms that aren't interested in technology, space exploration, or communication with other species. The universe might be full of intelligences that we wouldn't recognize and couldn't communicate with even if we encountered them. These speculations are fascinating but ultimately inconclusive. What matters is that we look, we listen, and we remain open to whatever we might find. FAST is helping us do that, and that's valuable regardless of whether we ever detect an artificial signal. The search itself teaches us about the universe and about ourselves. It forces us to think about life, intelligence, and technology in the broadest possible context. It reminds us that we're part of something much larger than ourselves or our world. Beyond the search for extraterrestrial intelligence, FAST's routine observations are revolutionizing our understanding of the radio universe. The telescope observes for thousands of hours each year, systematically surveying different regions of the sky, monitoring known pulsars to track their behavior over time, responding to targets of opportunity like newly discovered fast radio bursts or gamma-ray transients detected by satellite observatories. This steady drumbeat of observation is accumulating an unprecedented dataset that astronomers will be mining for years to come. Some of the most interesting science comes not from planned observations but from unexpected discoveries in archival data. Astronomers often go back through old observations looking for things that weren't the original target of the observation but happened to be in the field of view. As data processing techniques improve, it becomes possible to extract signals from old data that weren't detectable before. As theoretical understanding advances, astronomers know what new kinds of objects to look for. FAST's data archive is growing rapidly, and it will be a treasure trove for future discoveries. The telescope also plays an important role in multi-messenger astronomy, the practice of observing the same cosmic events using different types of signals. When gravitational waves from merging neutron stars were detected in August 2017, observatories around the world scrambled to observe the event at different wavelengths, from radio through optical to gamma rays. This coordinated campaign revealed an incredible amount of information about the merger and its aftermath. FAST can play a similar role in future multi-messenger campaigns, providing rapid radio follow-up to gravitational wave events, gamma-ray bursts, or other transient phenomena. Its sensitivity and rapid response capabilities make it an invaluable asset for this kind of time-domain astronomy. The science that emerges from FAST will take time to fully appreciate. Some discoveries are immediately recognized as important, but others only reveal their significance years later when they're combined with other observations or when theoretical understanding catches up. The history of astronomy is full of examples where observations sat in archives for years before someone realized their importance. Henrietta Leavitt's discovery of the period luminosity relationship for Cepheid variable stars in 1912 wasn't immediately recognized as one of the most important discoveries in astronomy, but it later became the foundation for measuring cosmic distances and discovering the expansion of the universe. Jocelyn Bell Burnell's detection of the first pulsar in 1967 was almost dismissed as interference before its true nature was recognized. What overlooked discoveries might be hiding in FAST's data? What phenomena are we detecting but don't yet recognize? What patterns are present but not yet understood? These are exciting questions because they suggest that the most important discoveries might not even be recognized yet. The data is there, waiting for the right person with the right idea to notice something everyone else has missed. The human side of FAST's story is worth emphasizing. Behind every discovery are people, astronomers proposing observations and analyzing data, engineers maintaining equipment and developing new capabilities, students learning their craft and making their first contributions to science, technicians working long hours to keep everything running smoothly. Large scientific projects like FAST require teams of people working together toward common goals, and the success of the project depends on everyone doing their part well. There's also an educational and inspirational dimension to projects like FAST. Young people in China and around the world see what FAST is accomplishing and are inspired to pursue careers in science and engineering. Teachers use FAST's discoveries to illustrate concepts in physics and astronomy. Science communicators share FAST's story with public audiences, helping people understand why this kind of research matters. In these ways, FAST's influence extends far beyond the scientific papers it produces. The telescope has become something of a tourist attraction as well, though access to the site is carefully controlled to minimize radio interference. Thousands of visitors come each year to view the telescope from designated viewing platforms, though they must leave their phones and other electronic devices behind before approaching the site. For many visitors, seeing FAST in person is a powerful experience, a tangible reminder that humanity is actively engaged in exploring the cosmos. The sheer scale of the structure is impressive in a way that photographs can't fully capture. Should we continue building even larger telescopes? FAST demonstrates what's possible with current technology and engineering techniques, but it also suggests what the limits might be. Building something significantly larger than FAST would face enormous challenges. The structural engineering becomes increasingly difficult as sizes increase. Finding a suitable natural depression would be harder. The costs would be staggering. Perhaps future radio astronomy will move in a different direction, using many smaller dishes working together as an array rather than ever larger single dishes. The Very Large Array in New Mexico and the Atacama Large Millimeter Array in Chile demonstrate the power of this approach. Or perhaps radio astronomy's future lies in space, with satellites carrying radio telescopes above the interference and limitations of Earth's atmosphere and ionosphere. Each approach has advantages and limitations. Single large dishes like FAST have maximum sensitivity and can observe a wide range of frequencies. Arrays can achieve very high angular resolution, allowing them to distinguish fine details, but typically have less sensitivity than a single dish of equivalent total collecting area. Space-based radio telescopes avoid Earth's radio interference but face challenges related to cost, complexity, and the difficulty of building and maintaining large structures in space. The future of radio astronomy will likely involve all of these approaches, each optimized for different types of observations. What's certain is that FAST has set a new standard for what's achievable in single-dish radio astronomy. Its discoveries over the next decades will shape our understanding of pulsars, neutron stars, fast radio bursts, the interstellar medium, neutral hydrogen in galaxies, and perhaps even reveal evidence of technological civilizations beyond Earth. The telescope stands as a testament to what humans can accomplish when we commit to ambitious goals and work together toward their achievement. Nan Rendon would have been proud to see what his telescope has accomplished and will continue to accomplish. Though he didn't live to see FAST reach its full potential, his vision is being realized every night as the telescope listens to the cosmos. The more than 1,000 pulsars discovered, the insights into extreme physics, the contributions to gravitational wave astronomy, the systematic survey of the radio sky, all of this flows from Nan's initial vision and his 2 decades of dedicated work to make that vision real. There's something moving about scientific legacies like this. The work continues long after the individual is gone. The telescope will operate for decades, probably longer. It will train new generations of astronomers. It will make discoveries that Nan never could have anticipated. In this way, his contribution to science will echo into the future, far beyond his own lifetime. That's a kind of immortality, perhaps the most meaningful kind, to create something that outlasts you and continues contributing to human knowledge and understanding. As FAST continues its observations, as the catalog of discovered pulsars grows, as fast radio bursts are localized and studied, as the search for extraterrestrial intelligence continues, we're reminded that science is an ongoing process. Each discovery raises new questions. Each answer leads to deeper mysteries. We learn more and more about the universe, but our increased knowledge often reveals how much more there is to learn. FAST is helping us push back the boundaries of ignorance, but beyond those boundaries, the universe stretches on, vast and full of wonders we haven't yet imagined. The 500-meter aperture spherical radio telescope, China's celestial eye, stares into the cosmos night after night, listening patiently for signals from distances almost impossible to comprehend. It hears the regular pulses from dead stars, rotating hundreds of times per second yet stable enough to rival atomic clocks. It detects mysterious bursts of energy from billions of light-years away. It maps the distribution of hydrogen gas in distant galaxies. It searches for whispers that might indicate we're not alone. And in doing all of this, it reminds us that humanity, for all our limitations and flaws, is capable of extraordinary things when we set our minds to understanding the universe we inhabit. The landscape surrounding FAST has remained largely unchanged for millions of years. The karst formations in Guizhou province developed slowly through geological processes, as slightly acidic rainwater dissolved the limestone bedrock, creating a terrain of depressions, caves, and underground rivers. Then, in the span of just a few years from a geological perspective, humans arrived and transformed one of these depressions into the most sophisticated radio telescope ever built. The contrast is striking, ancient geology meeting cutting-edge technology, the patient work of erosion and dissolution meeting the urgent drive of human curiosity. The choice of this particular depression among the many available in the region involved extensive surveying and analysis. The engineers needed a depression that was large enough to accommodate the 500-meter dish, with the right depth profile to minimize the amount of additional excavation required. The surrounding terrain needed to provide natural shielding from radio interference. The bedrock needed to be stable enough to support the telescope's foundation and the towers that support the cables holding the receiver cabin. Access needed to be feasible for construction equipment and ongoing operations, even though the site would remain remote enough to minimize interference from human activity. Finding a location that satisfied all these requirements took years of searching and careful evaluation. Once the site was selected, the construction phase presented its own set of challenges. The region's climate, with its distinct wet and dry seasons, affected when certain types of work could be performed. Heavy rainfall during the wet season made access difficult and could destabilize soil and rock. The remote location meant establishing temporary infrastructure to house workers, store materials, and provide power and water. Environmental concerns had to be addressed to minimize the impact on the local ecosystem. And of course, there was the human element, the villages that needed to be relocated, the people whose lives were disrupted by this massive scientific project. The relocation of over 9,000 people is perhaps the most controversial aspect of FAST's construction. These were communities that had lived in the area for generations, farming the land and following traditional ways of life. The creation of a radio-quiet zone around the telescope required moving these people away from their homes. The Chinese government provided compensation and built new housing for the relocated residents, but such relocations inevitably involve loss of familiar surroundings, loss of community connections, loss of ancestral lands. Some relocated residents adapted well to their new circumstances, while others struggled. This human cost is part of FAST's story, and it raises questions about the price we're willing to pay for scientific advancement. Similar issues have arisen with other major observatories. The construction of telescopes atop Mauna Kea in Hawaii has been controversial because the mountain is sacred to native Hawaiians, and the presence of telescopes is seen by some as desecration of a holy site. The 30-meter telescope project has faced protests and legal challenges for years. In Chile, astronomers have had to negotiate with indigenous communities about access to sites for observatories. These situations highlight the tension between the universal value of scientific knowledge and the particular values and rights of local communities. There are no easy answers. But increasingly, the scientific community recognizes the need for genuine consultation, respect for local concerns, and equitable sharing of benefits. In FAST's case, the creation of an astronomy-themed tourism industry in the area has provided some economic benefits to offset the disruption caused by the telescope's construction. Viewing platforms allow visitors to observe the telescope from a distance. Museums and educational centers explain FAST's science and technology. Hotels and restaurants serve the tourists who come to see this engineering marvel. These developments have created jobs and brought money into the local economy. Whether this adequately compensates for what was lost is a question each affected person must answer for themselves. The technical specifications of FAST continue to impress even years after its construction. The 4,450 triangular panels that form the reflective surface are each made of perforated aluminum, allowing air to flow through and reducing wind load while still reflecting radio waves. The panels are connected to a supporting mesh of cables, with approximately 2,800 actuators controlling their position. These actuators can adjust the panel positions with millimeter precision, allowing the surface to reconfigure its shape within minutes. This active surface control is essential for pointing the telescope at different parts of the sky and maintaining the focusing properties of the reflector. The receiver cabin suspended above the dish houses the actual radio receivers that collect the signals focused by the reflector. This cabin weighs approximately 30 tons and hangs from cables attached to 6 towers surrounding the depression. The cabin can move to any position within a radius of approximately 200 meters, allowing the telescope to observe different parts of the sky. Inside the cabin are receivers operating at different frequencies, from low frequencies around 100 MHz up to several gigahertz. Different receivers are optimized for different types of observations. Pulsar searches typically use frequencies around 1.4 GHz, where pulsar emission is often strong and the effects of the interstellar medium are manageable. Neutral hydrogen observations use frequencies around 1.42 GHz, the characteristic emission line of hydrogen atoms. The signal processing chain for FAST involves multiple stages of amplification, filtering, and digitization. The radio signals collected by the receivers are extremely weak, often just a few femtowatts, that's a few quadrillionths of a watt. These signals must be amplified by factors of millions while adding as little noise as possible. The amplified signals are then filtered to select specific frequency ranges and digitized, converting the analog radio signals into digital data that computers can process. The digital data streams are synchronized with atomic clock timing signals to ensure precise time stamps for every observation. This timing precision is crucial for pulsar observations, where astronomers need to measure pulse arrival times with microsecond or even nanosecond accuracy. One of the challenges in radio astronomy is dealing with radio frequency interference, or RFI. We live in a world saturated with radio emissions from human technology, cell phones, Wi-Fi routers, satellites, aircraft radar, television and radio broadcasts, microwave ovens, and countless other sources. All of these emit radio waves that can swamp the faint cosmic signals astronomers are trying to detect. Radio observatories go to great lengths to minimize RFI, locating in remote areas, implementing radio quiet zones, and using sophisticated signal processing to identify and remove interference from the data. Even so, RFI remains a persistent problem. As our technology proliferates and more of the radio spectrum is used for communications, finding clean radio windows for astronomy becomes increasingly difficult. FAST's remote location and the radio quiet zone surrounding it help with RFI, but they don't eliminate it entirely. Satellites passing overhead still emit signals. High-altitude aircraft may be detectable. Even lightning from distant thunderstorms can produce radio emissions. The data processing pipeline includes automated RFI detection algorithms that identify signals with characteristics inconsistent with cosmic sources. These might be signals that appear only at frequencies used by human technology, or signals that appear and disappear too quickly to be astronomical, or signals that show up in only some of the telescope's receivers but not others. Identifying and removing RFI without losing genuine cosmic signals requires careful analysis and constant refinement of the algorithms. The operation of FAST follows a model common to many large astronomical facilities. Astronomers submit proposals describing the observations they want to make and the scientific goals they hope to achieve. These proposals are evaluated by committees of experts who assess the scientific merit of each proposal and the feasibility of the observations. The highest-rated proposals are awarded observing time. The actual observations are then typically carried out by professional telescope operators following instructions specified by the astronomers. The raw data is processed through standard pipelines and made available to the astronomers who proposed the observations. After a proprietary period, often around 1 year, the data becomes publicly available so that any astronomer can use it. This model democratizes access to expensive facilities like FAST. An astronomer at a small university with no observatory of their own can propose observations and, if their proposal is competitive, get access to one of the world's premier telescopes. This helps level the playing field and ensures that good ideas from anywhere can be pursued. Of course, the system isn't perfect. Well-known astronomers with track records of important discoveries may have an advantage in getting their proposals accepted. Astronomers from institutions in wealthy countries may have more resources to develop competitive proposals. The peer review process, while generally fair, is still subject to human biases. But compared to a system where access to telescopes is restricted to a privileged few, the open proposal system is a significant improvement. The scientific productivity of FAST can be measured in several ways. The most straightforward metric is the number of papers published using FAST data. By the end of 2024, several hundred papers have been published based on FAST observations, covering topics from pulsar timing to fast radio bursts to neutral hydrogen surveys. These papers appear in leading journals and are cited by other researchers, indicating that FAST's results are having an impact on the broader astronomical community. Another metric is the number of new objects discovered, like the 1,000-plus pulsars already mentioned. Yet another is the contribution to large collaborative projects like pulsar timing arrays or multi-messenger astronomy campaigns. By all these measures, FAST is proving to be enormously productive. But scientific impact isn't always immediate or easily quantified. Some of the most important contributions from FAST may not be recognized for years. Perhaps FAST is detecting signals that will only make sense once we develop new theoretical frameworks. Perhaps patterns in FAST's data will only become apparent once combined with observations from future facilities. Perhaps the most important discovery will be made by a graduate student analyzing archival FAST data 10 years from now, long after the original observation was made. The full scientific legacy of FAST won't be clear until decades into the future. The educational impact of FAST is already significant. The telescope has inspired a new generation of Chinese students to pursue careers in astronomy and astrophysics. Universities in China have expanded their astronomy programs to train the scientists needed to analyze FAST's data and develop future facilities. International collaborations have brought Chinese astronomers into contact with colleagues around the world, fostering exchange of ideas and techniques. Summer schools and workshops held at the FAST site have trained hundreds of young scientists in radio astronomy techniques. These educational activities ensure that the expertise needed to operate FAST and similar facilities will be available in the future. There's also a public engagement dimension to FAST that shouldn't be underestimated. Millions of people in China and around the world have learned about FAST through news articles, documentaries, social media, and other channels. For many, FAST is their first exposure to radio astronomy or even to astronomy in general. The telescope captures the public imagination in a way that more abstract scientific achievements sometimes don't. There's something tangible and impressive about a 500-meter dish that makes the science accessible. People can visualize the telescope, understand at a basic level what it does, and appreciate the technological achievement it represents. This public engagement helps build support for science and reminds people that humanity is engaged in something grander than just our day-to-day concerns. The comparison between FAST and other major radio telescopes around the world is instructive. The Very Large Array in New Mexico consists of 27 individual dish antennas, each 25 meters in diameter, arranged in a Y-shaped configuration. The dishes can be moved along railroad tracks to change the spacing between them, allowing the array to function as a single telescope with variable resolution. The VLA has made countless important discoveries over its 4 decades of operation, from imaging jets of material ejected by black holes to mapping the radio emission from supernova remnants to detecting neutral hydrogen in distant galaxies. The VLA demonstrates the power of arrays, where many smaller telescopes work together to achieve capabilities no single telescope could match. The Atacama Large Millimeter Array, or ALMA, located in Chile's Atacama Desert at an altitude of 5,000 meters, consists of 66 dish antennas observing at millimeter and submillimeter wavelengths. ALMA's high altitude puts it above much of Earth's water vapor, which absorbs millimeter wavelength radiation. This allows ALMA to observe at wavelengths that are impossible from sea level. ALMA has revolutionized the study of planet formation, observing the disks of gas and dust around young stars where planets are being born. ALMA images show gaps and rings in these disks, likely carved out by forming planets, providing direct observational evidence of the planet formation process. ALMA also observes the molecular gas in galaxies, tracing the raw material from which stars form. The Square Kilometre Array, or SKA, currently under construction in Australia and South Africa, will be the world's largest radio telescope array when completed. The SKA will consist of thousands of individual antennas spread over distances of thousands of kilometers, functioning together as a single telescope with a total collecting area of 1 square kilometer, hence the name. The SKA will have unprecedented sensitivity and will be able to map the distribution of neutral hydrogen across cosmic history, trace the formation and evolution of galaxies, detect enormous numbers of pulsars, and search for gravitational waves and fast radio bursts. The SKA represents the next generation of radio astronomy facilities, and it will complement FAST's capabilities. Each of these telescopes has different strengths. FAST's enormous collecting area gives it unmatched sensitivity for detecting faint signals, making it ideal for pulsar searches and SETI. The VLA's ability to reconfigure its array provides flexibility in balancing sensitivity and resolution. ALMA's high-frequency capabilities allow it to probe cold dust and molecular gas invisible at longer wavelengths. The SKA's massive collecting area and advanced technology will push the boundaries of what's possible across a wide range of science. Rather than competing, these facilities complement each other, and astronomers often use multiple telescopes to study the same objects at different wavelengths and with different techniques. The phenomenon of fast radio bursts, or FRBs, deserves more detailed discussion because FAST is playing a crucial role in unraveling this mystery. The first FRB, designated FRB 010724, was discovered in archival data from the Parkes Observatory by Duncan Lorimer and his student David Narkevic in 2007. The burst lasted just 5 milliseconds but was bright enough to be detectable from a distance of billions of light-years. The brief duration and large distance implied an enormous energy release, comparable to what the Sun emits in several days, all packed into a few milliseconds. This was so surprising that many astronomers initially thought there must be a more mundane explanation, perhaps some kind of terrestrial interference or instrumental artifact. But as more FRBs were discovered by other telescopes, it became clear that these were real astrophysical phenomena. For years, FRBs were detected but not localized well enough to identify their host galaxies or determine exactly where they were coming from. This made it difficult to study them in detail or understand what produces them. Then in 2016, an FRB designated FRB 121102 was detected that repeated. Unlike most FRBs which are observed only once, this particular source produced multiple bursts over time. This repeatability allowed astronomers to study it more carefully and eventually localize it to a dwarf galaxy about 3 billion light-years away. This was a breakthrough because it ruled out models where FRBs were produced by one-time catastrophic events like colliding neutron stars. Whatever produces at least some FRBs, it must be something that can repeat. FAST has detected numerous FRBs, including several repeating sources. One of FAST's most significant contributions was detecting many repeat bursts from FRB 120520b, also known as FRB 180916. FAST observed this source producing multiple bursts within short time periods, sometimes dozens of bursts in a single observing session. The high sensitivity of FAST allowed detection of fainter bursts than other telescopes could see, providing insights into the range of burst energies and properties. The data showed that some repeating FRBs can be extremely active, producing bursts at rates much higher than previously observed. This suggests that the burst emission mechanism can operate rapidly and repeatedly, providing constraints on theoretical models. The leading theory for at least some FRBs involves magnetars, neutron stars with extraordinarily strong magnetic fields. Magnetars are known to produce powerful bursts of X-rays and gamma rays, and theoretical models suggest they could also produce radio bursts under certain conditions. In April 2020, an FRB-like burst was detected from a known magnetar in our own galaxy, SGR 1935+2154. This was the first time an FRB-like event had been detected from a known astrophysical source, and it strongly supported the magnetar model for at least some FRBs. However, it's not yet clear whether all FRBs are produced by magnetars or whether multiple mechanisms might be responsible for different types of FRBs. The dispersion of FRB signals provides information about the ionized gas they've passed through on their journey to Earth. The amount of dispersion, characterized by the dispersion measure, tells us approximately how far the burst has traveled through ionized material. For FRBs coming from distant galaxies, most of the dispersion comes from the intergalactic medium, the tenuous gas between galaxies. By studying the dispersion of many FRBs, astronomers can probe the distribution and properties of this intergalactic gas, which is otherwise very difficult to observe. FRBs are thus not just interesting in themselves but also serve as probes of the matter between galaxies. Some FRBs show complex time structure with multiple subbursts or evidence of scattering by material near the source. This scattering can provide clues about the environment where the FRB originates. If the FRB source is embedded in a dense, turbulent plasma, the burst will be scattered and broadened in time. By analyzing this scattering, astronomers can infer properties of the plasma near the source. Some repeating FRBs show evolution in their scattering properties over time, suggesting changes in the environment around the source. FAST's high time resolution and sensitivity make it well suited for detecting and characterizing this structure. The polarization of FRB signals is another important property that FAST can measure. Radio waves are electromagnetic waves, and like light, they can be polarized, meaning the electric field oscillates in a particular direction. By measuring the polarization of FRBs, astronomers can learn about magnetic fields near the source and along the line of sight. Some FRBs show high degrees of linear polarization, sometimes nearly 100%, indicating that the emission mechanism is highly organized. The polarization angle can rotate as the radio wave propagates through magnetized plasma, a phenomenon called Faraday rotation. By measuring this rotation, astronomers can estimate the strength and structure of magnetic fields in the FRB host galaxy and in the intergalactic medium. FAST's discoveries are contributing to a rapidly evolving picture of what FRBs are and where they come from. It seems likely that multiple types of sources can produce FRB-like bursts. Magnetars are probably responsible for many FRBs, particularly the repeating ones, but other mechanisms might contribute as well. Some models invoke mergers of compact objects, supermassive neutron stars that collapse to black holes, or other catastrophic events. As more FRBs are discovered and studied in detail, the taxonomy of FRBs will become clearer, and will develop a better understanding of the underlying physics. The rate at which FRBs occur is itself an interesting question. Early estimates suggested thousands of FRBs might be occurring across the entire sky every day, but we can only detect a tiny fraction of them because most are too faint or occur when we're not observing the right part of the sky. As telescopes like FAST survey larger areas of sky with greater sensitivity, we're detecting more and more FRBs and getting better statistics on their rate and properties. Understanding the FRB rate helps us estimate how many sources exist in the universe and provides another constraint on theoretical models. The future of FRB science looks bright. New facilities coming online, including the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, and the Deep Synoptic Array in California, are specifically designed to detect and localize large numbers of FRBs, combined with FAST's unmatched sensitivity for detailed follow-up observations. These facilities will provide a comprehensive view of the FRB population. Within a few years, we may have detected thousands or even tens of thousands of FRBs, enough to do detailed population studies and test theoretical models rigorously. FAST will continue to play a central role in this research, providing the detailed observations needed to understand the most interesting sources. Neutral hydrogen observations represent another major area where FAST is making contributions. Hydrogen is the most abundant element in the universe, and much of it exists in the form of neutral hydrogen atoms, particularly in the interstellar medium of galaxies. Neutral hydrogen atoms emit radio waves at a very specific frequency corresponding to a wavelength of 21 centimeters. This emission occurs when the spin of the electron in the hydrogen atom flips relative to the spin of the proton in the nucleus. This is an extremely unlikely event for any individual atom. It might happen once every 10 million years on average, but because there are so many hydrogen atoms, the cumulative emission is readily detectable. By observing 21 centimeter emission, astronomers can map where neutral hydrogen exists in galaxies and how it moves. Since hydrogen is the raw material from which stars form, understanding its distribution is crucial for understanding star formation and galaxy evolution. FAST can detect neutral hydrogen emission from nearby galaxies, tracing their structure and kinematics in detail. For more distant galaxies, where the 21 centimeter emission is redshifted to longer wavelengths, FAST can detect hydrogen that we're seeing as it was billions of years ago, providing insights into how galaxies evolved over cosmic history. One of FAST's goals is to conduct large-scale surveys of neutral hydrogen in galaxies across a range of distances. These surveys will provide a census of the hydrogen content of the universe at different epochs, showing how the amount and distribution of neutral hydrogen has changed over time. Since neutral hydrogen is converted into stars through the process of star formation, tracking the hydrogen content over cosmic history helps us understand when and where stars formed, and how the star formation rate has evolved. This is a key part of the larger story of cosmic evolution, from the simple, uniform universe shortly after the Big Bang to the complex, structured universe we observe today. FAST can also detect neutral hydrogen in the Milky Way, our own galaxy. Mapping the distribution of hydrogen in the Milky Way helps us understand our galaxy's structure, including the spiral arms where stars and gas concentrate. The motion of hydrogen gas traces the rotation of the galaxy and reveals the presence of dark matter, the mysterious invisible substance that exerts gravitational effects but doesn't emit light. By measuring how fast the galaxy rotates at different distances from the center, astronomers can infer how mass is distributed, including the dark matter that makes up most of the galaxy's mass. FAST sensitivity allows it to detect even faint, diffuse clouds of hydrogen that might be missed by other telescopes. The interstellar medium, the gas and dust between stars, is itself a rich target for study. This medium is far from uniform. It contains cold, dense clouds where stars are forming, warm diffuse gas, hot ionized bubbles created by supernova explosions, and complex structures shaped by the combined effects of stellar winds, supernova shocks, magnetic fields, and gravity. Radio observations at 21 centimeters probe the neutral component of this medium, complementing observations at other wavelengths that trace different components. By building up a comprehensive picture of the interstellar medium, astronomers can better understand the life cycle of matter in galaxies, from gas to stars and back to gas again. Supernova remnants, the expanding shells of material ejected when massive stars explode, are particularly interesting objects that FAST can observe. These remnants emit radio waves through synchrotron radiation, produced when electrons spiral through magnetic fields at relativistic speeds. The remnants expand into the surrounding interstellar medium, creating shock waves that heat and compress the gas. Over thousands of years, the remnants fade and merge with the general interstellar medium, enriching it with heavy elements produced in the supernova explosion. Observations of supernova remnants provide insights into the explosion mechanism, the properties of the ejected material, and the structure of the surrounding medium. FAST sensitivity allows it to detect faint remnants and study their properties in detail. The synergy between FAST and other astronomical facilities extends beyond just radio telescopes. Optical telescopes can identify stars and measure their properties. Infrared telescopes can see through dust and observe star formation in action. X-ray telescopes detect hot gas and energetic phenomena. Gamma-ray satellites observe the most energetic processes in the universe. By combining observations from across the electromagnetic spectrum, astronomers build comprehensive pictures of astronomical objects and phenomena. FAST's radio observations are a crucial piece of this multi-wavelength puzzle. Consider a supernova, for example. When a massive star explodes, it produces a brilliant optical display that can briefly outshine an entire galaxy. Optical telescopes observe the light curve, how the brightness changes over time, and analyze the spectrum to determine the composition of the ejected material. X-ray satellites detect the hot shock waves generated by the explosion. As the remnant expands and ages, radio telescopes like FAST can detect the synchrotron emission from relativistic electrons in the remnant. Years or decades after the explosion, infrared telescopes might detect dust forming in the cooling ejecta. By following a supernova across its entire life cycle and observing it at multiple wavelengths, astronomers can test models of stellar evolution and the explosion mechanism. The same multi-wavelength approach applies to many other phenomena. Active galactic nuclei, powered by supermassive black holes accreting material, emit across the entire electromagnetic spectrum. Radio observations trace jets of particles ejected at nearly the speed of light. Optical observations might reveal the accretion disk and emission from gas in the galaxy. X-rays come from the hot gas near the black hole. Gamma rays might be detected if we're looking directly down the jet. Each wavelength provides different information, and only by combining them all can we fully understand what's happening. FAST contributes the radio piece of this puzzle, and often the radio observations are crucial for identifying jet structures or detecting sources that are faint at other wavelengths. The practical challenges of operating FAST deserve mention. Radio telescopes are delicate instruments that require constant maintenance and calibration. The reflective surface must be kept clean and properly aligned. The cables supporting the receiver cabin need regular inspection for wear and damage. The electronic systems require calibration to ensure accurate measurements. Environmental factors like wind, temperature changes, and lightning can affect observations and potentially damage equipment. The telescope operates 24 hours a day, year-round, with only minimal downtime for maintenance. This requires dedicated teams of operators, engineers, and technicians working around the clock.